EERIE stands for European Eddy-RIch Earth System Models. As I indicated before, it's really about, pushing the boundaries of resolution with the view of, explicitly resolving mesoscale features in the ocean and sea ice, the ocean, sort of the weather of the ocean, if you will. And I think, a lot of what is possible and what we are able to do now is certainly due to technological developments. And here you see these sort of well-known increases in performance as a function of time, with some indication of leveling off very recently, perhaps with the exception of just the biggest machine, the top-ranked machine here in this list. Now here's an animation. We have seen probably similar ones before of the ocean currents here. With the model that we have developed at ERVI, and we clearly showing that we can produce simulations of eddy-rich oceans. But I think what's very important also for EERIE really is that these models can generate now a throughput of something of 10 or so, with pushing it probably 10 simulated years per day. So that's certainly within reach. Okay. And I think that's really good news, because that means, that we can go from showing nice animations that look very beautiful and, and analysis that is qualitative, we can move towards quantitative understanding. Okay, we can run now in a matter of 10 days or so, we can run a full, first 21st century, I mean, certainly with an ocean-only configuration. We will be addressing this question in EERIE, but sort of where do we stand on this? What's the status quo? And this is a graphic that we used for our proposal. On the lower left, you see sort of a typical CMIP type model. In the upper one, you see surface currents from altimeter data, from satellite data. And in the lower right, you see something we would term eddy-rich in the North Atlantic. And I think that the message is, these kind of models start to be indistinguishable from satellite data. So you may say they passed the so-called, climatic Turing test. And I think that's very promising. Whether that means that things in the coupled setup sort of near the grid scale and, whether this is realistic, that remains to be shown. And that's one of the tasks we want to, work on in EERIE for sure. Sort of the overarching goal is really to reveal and quantify the role of ocean mesoscale processes, the ocean weather, in shaping the climate trajectory. And when I talk about the ocean here, we always mean ocean and sea ice as well. Now we want to develop and test a new class of models that are eddy-rich, and we also want to improve and sort of the workflows. So we want to improve in that context also the technical and climate readiness of the system. So technically, and being able to run and do this in an efficient way, and climate readiness, we have to say, and I come back to the models a little bit later, that some of them are rather new developments, where still some basic developments have to be done. And then last but not least, we want to determine how scale interactions associated with exchanges at the mesoscale govern the risk of changing risk of weather and climate extremes and tipping points as well worldwide. How are we going to accomplish our goals? Now, one is certainly bringing leading experts together. And I don't want to go through this list of consortium members. We have in total, we have 12 partners from Europe that are listed here. And we have also, I'm very pleased to say, 2 partners from Africa as well. Then we have our 5 associated partners, 2 from the UK with their own funding. And then we have ETH from Zürich, which also brings its own funding. Now, does it matter is also, we described this a little bit as, possible climate surprises. So the idea is, if we take eddy-rich models that are sort of computationally more challenging and expensive, does it perhaps, change our understanding of what's coming our way in a warming climate? And here you see temperature projections on the right-hand side with a typical CMIP 6 type configuration. And on the left-hand, one where you could say regionally we start to be eddy permitting. And there are certain things that seem to be independent of resolution resolution changes done here. But I mean, certainly when you look into the Southern Ocean, the answer is completely different. Where CMIP 6 type models say it should warm, and it should have warmed already by now. High resolution type simulations suggest, the warming is delayed probably well into the 21st century. So now these high resolution runs on the left-hand side, sort of they are early runs, and it will really be interesting to see, whether our simulations will, shed a bit more light on whether going eddy-rich in the southern regions will be a game changer in terms of predicting the fate of the Southern Ocean and the climate system as a whole. We will use Eddy-RIch Earth System Models to try to understand the role of and impact of mesoscale processes on climate in a warming world. And the ultimate goal is to provide more trustworthy climate change projections in support of adaptation.
I just want to say that I'm extremely happy to see this start. It was a lot of work, but I think the ideas that we introduced, this revolution that happened in the atmosphere now moving into the ocean, we've been trying to get something like this together for a long time, and I think it's very wise of the European Commission to have funded this. If I may be so immodest as to say that. I think this is really exciting. As you say, there's an incredible synergy across many projects, and they're all coming together in different ways, but they all have the same fundamentals ideas behind them. And I think this is a great time for this to be happening, and I really look forward to it.
So this is meant to be a group of people who can advise us from outside the project, can kind of see what the project's doing, but also what they're involved in the wider community, and kind of help us to link those two things together, as well as advise us on kind of particular things we're doing, because they have a kind of broad range of expertise. So the kind of functions of the EAB is to advise on our scientific approach and orientation, to advise and assist us on dissemination, so this kind of linking to different communities, so we don't kind of sit in our kind of European climate bubble that we try and go out into the wider community, to link to those related activities both inside and outside of Europe, to provide international perspectives on the kind of development of Earth system models, and again how we fit in that, how we push those boundaries as Thomas has been talking about, and kind of make recommendations on any new actions and initiatives in our area that are going on that we should know about and we should find out about, and maybe that we should interact with.
It's pretty obvious that one main motivation for data management comes out of the high volume, high resolution Earth system model output that we are generating here in EERIE, and that demands for an effective data management in order to enjoy high scientific value of this data set that we are going to produce.
What we see here is that they identified eddies within the Southern Ocean, quite a number of them, and over anticyclonic warm eddies, we have these warm anomalies that can actually destabilize the overlying atmosphere, so it helps in transferring momentum from winds aloft to the surface in such a way that over warm anomalies you can have faster wind speeds, but not only that, the warm surface temperature imprints on the atmosphere in a way that it can deepen the atmospheric boundary layer. And here you can see there's that deepening of it, and therefore that allows more cloud formation above it, as well as precipitation. So you can see already that there's this coupling between the ocean and the atmosphere. And conversely, it's true if you have a cold anomaly instead, so cold cold core eddies, this can basically enhance the stability of the atmosphere above it, so you have slower winds, but also it causes I guess you can call it a shallowing of the boundary layer, and that would inhibit cloud formation and also inhibit precipitation. So this is work that's already been seen, and this is what we want, and it's of course seen here now in observations. And what we want to do is to test and see if we can see these types of phenomena and processes within the climate model itself that we're running.
The idea is to quantify the integrated effects of eddies at interannual to decadal timescales, and considering heterogeneities of the ocean mix layer, the upper ocean stratification, ventilation and deep water formation, and how those processes are going to change in the future. I mean, this is really well illustrated by this image of eddies in the Labrador Sea. I mean, as you all know, the Labrador Sea is one of the hotspots for deep water transformation in the world ocean. And of course, these transformations are shaped by the eddies.
And the model data sources we'll be using to inform this analysis, we have the Eddy-RIch frontier simulations, which will be, so these are the main EERIE experiments, which will be coming from work package 4. We also have some idealized atmosphere-only model simulations with different sea surface temperature boundary conditions. And hopefully these will allow us to do some more causal interpretation of the local versus remote drivers of mesoscale SST variability. And then, as Anne-Marie just mentioned, these EERIE datasets won't be available immediately, so we also need to think about which other datasets are available from other projects like HiResMIP and Primavera or other complementary datasets that are already available.
And the idea is to see if we have a different understanding from these eddy resolving models on how the climate change is going to unfold, and to try to link it back to the main mechanisms that have been described from the other work packages. At the bottom, we are showing the position of the Gulf Stream, and you can see that in the Eddy-RIch simulations, this position is moving, is shifting northward as the climate is warming, which is not happening in the eddy permitting one. And we also see that there is a big change between these two periods, like a massive warming over the same region, which is also associated with changing in its intensity. The consequence that we could see in this simulation, was that as the Gulf Stream position was moving northward, the storm tracks were moving as well, and there was a big increase in winter precipitation over Europe, which was not matched by the other model.
Running these very high resolution coupled models is obviously really interesting and important, but it's often very difficult to explain, well, okay, we see a response over Europe, but is that because we've improved the Gulf Stream or the air-sea interactions in the proximal North Atlantic region, or is it because we've made some changes in the tropics, which have been very efficiently communicated by Rossby waves and global teleconnections? So the idea here is that we do some additional experiments that can complement the EERIE frontier integrations and help us really specifically address some of these questions. And here we will deliver this data in month 24. And I really hope we're able to use this routinely within work packages 5 and 7, especially whilst people are looking at the frontier integrations, that we provide this data in the same way, so we can have this complementary analysis of the idealized experiments and the atmosphere-only uncoupled experiments.
What are we going to address in EERIE? I mean, there will be some playing around, I would call it, with domain-specific languages. I think we will be seriously looking into certain aspects of the usage of GPU. Nothing radical in refactoring the models, but sort of more using OpenACC and try to see what's possible on what could be considered a fast track. I think a very interesting area will be the exploring the impact of reduced precision configurations. And I think, people have learned a lot about single precision in the atmosphere, but, trying this for the ocean and sea ice, and this then in long runs where errors can accumulate more slowly. I think this will be an interesting task, but in principle, the gain here could be quite large. One could expect something like a 40 or 50% speed up, by using single precision. I mean, these are the kind of speed ups that ECMWF has experienced in their operational forecasting system. And then, working on output CI solvers in principle, in general, and also providing tools to assess and reduce bottlenecks is quite important.
We want to be able to reduce the data that comes out of the model, doing the diagnostics as soon as possible to avoid this huge data volume that we will be generating, and also to increase the velocity at which the scientist will be able to analyze the simulations. For that, we will also develop some standalone solutions and data processing workflows. So a very long sentence, an official sentence to say that what we will do is to separate the different parts of the workflow, of the analysis, of the diagnostics, in a way that can be reproducible and that can be containerized.
So what we do in this workshop is we apply machine learning techniques to improve some of the ERIE models and to make them faster.
So we have three main objectives, the first of which is to develop the next generation of Earth system models, bringing together process realism and increased model resolution. So why process realism? Because we need answers to questions that we have to use full Earth system models to be able to answer such questions. Questions such as how fast is the ice in Greenland, in the Antarctica melting, and how fast will it melt in the future? What does this melting mean for sea level rise and for ocean circulation? Questions like how much CO2 is released by dying tropical forests? How much CO2 will the land, the ocean, and the vegetation absorb in the future under a warmer climate? And how will these changes affect the remaining carbon budget?
Here we have the time in years we simulate, and this dot is EERIE, what is done roughly right now, and that's NextGEMS, that's what we're doing right now, and these are some other configurations we are running. And EERIE will push this boundary up by running much longer timescales. So I marked here around 700 years, which I think is roughly the total number of years which will be simulated in EERIE according to the protocol.
In terms of synergies, yesterday I already mentioned that it's expected, or I would say mandatory from a PO point of view, the establishment of synergies with other projects. Here I have some indications, but most of them you are already aware. Optimism and the sister project under this topic, but also other projects like ESM 2025, NextGEMS. Here I included others that could be of interest. Well, I still have ETH here in the list, but okay. It's also important, and this I will definitely encourage during the project lifetime, synergies with a recently started project, Eddy-RIch Model Lab, which is coordinated by Mercator International, and it aims to develop some components of the digital twin of the ocean, which definitely I consider that ETH can contribute in a very close way with this project.
The engine of the project, basically where the science goes on and where science is discussed and the important issues, that will be the scientific steering committee. We have on board one work package leader of each work package plus the co-leader, and they have quarterly management meetings which are also chaired by the coordinator.
Data protection is a very important topic as well. I know that we talked about fair data, open research data, etc., but please be aware that if you use sensitive data, personal data, to mind the general data protection regulation, and keep cybersecurity in the back of your minds as well.
And with this at 13:60, so with a delay of 1 minute, I'm happy to close the EERIE kickoff meeting. And I wish all of you a wonderful weekend.